Hi, this is Travis Tran,
And I'm Kevin Vo.
and our presentation is about deep structure inference network for facial action unit recognition. This research was done by the people listed on the slide below, and this research is still ongoing. So, quick introduction about facial expressions and why this research was important to that. So, facial expressions represent one of the most important cues in recognizing nonverbal behavior, being important in a part of human social signaling. So rather than just talking, maybe like in a movie or something, you can recognize people's emotions by their facial expressions, something like that. And the ability to automatically mine those human intentions, attitudes, or experiences has potential in a lot of ways, such as improving on e-learning experiences or creating AIs in games to mimic the human intentions more accurately, um, detecting human pain or pain in general, monitoring patients through like a monitor rather than not being there in person. Even in police interrogations, if they start to lie, it can detect deceptions using the something like this, or even in job interviews. Um, these are a few applications the study would benefit. So the problem is how to deal with action unit recognition. Hash learning and multi-label learning are related to the deep structured inference network. These are problems that deal with temporal features or representation learning. The, in the recent years, most efforts in automatic action unit recognition have been dedicated to learning combinations of local features and to exploit correlations between these action units. In this research, the people that did this, they proposed a deep neural architecture that tackles both problems by combining learned local and global features in its initial stages, and then it replicated the message, passing it through an algorithm between classes similar to a graphic model. Uh, this would approach this would be approached in later stages. Um, so to gauge how well their research research has done, they use the training model BP4D and DISFA. These data sets. BP4D is a multimodal spontaneous emotion corpus. This contains multimodal data sets that include synchronizing 3D, 2D, thermal, physiological data sequences, as well as metadata, which is facial features. And then the other data set they used was DISFA, which is Denver Intensity Spontaneous Facial Action Database. Is a that is a non-posed facial expression database for those who are interested in developing computer algorithms for computer action unit detections. So action units, or AUs, as they would always abbreviate, are patterns of muscular activation, activation and the way they modify facial morphology and is relatively localized on the face. So in the pictures below, starting from the top left, uh, those are just the neutral pictures without any, they're just the pictures of the faces. And then by masking just a small region of the neutral faces, they become indistinguishable from what they were. So comparing the top part to the bottom, once they block out that just small region of the face, they can't. The program was not able to recognize between the two for all those four examples. And then also when comparing the images, they can also several of the action units can be active at the same time. So also in those data sheets, they're also correlated to the FAUS, which is a facial action unit system. This is a descriptive coding scheme of facial expressions that focus on what the face can do without assuming any cognitive or emotional value. So it could probably tell what kind of emotions without having any background sort of thing. They're measured in components of action units, and they're combined just to form a complete representation of the facial expression. These, action units are patterns of the muscular. Oh, I already said that. Recognizing these action units are important in developing general facial expression analysis. So patch learning, on the next slide. This is a simple figure about patch learning. So first of all, patches are small portions of the image. As you see in the middle portion, there's about 8 patches. So using patch learning, you can find, parts, kind of like a parts of the puzzle to figure out the original image. In this methodology, finding the same individual in the network of cameras, so imagine if you took multiple pictures of the same object, just in different locations, they need to be variated in illuminating with viewing angles, and have to be consistent with the person's pose. Re-identification requires solving the 2 fundamental problems: determining the distance between features extracted from the cameras with the changes, and ensuring that matched features refer to the same body. So making sure, they're part of the same object, whatever you're trying to patch together. In this research, patch location was predefined and didn't take into account facial geometry, and also patch location is locally connected by convolutional layers and propose an immediate regional connection that learns specific convolutional filters from sub-areas of the input. So on to the next slide, multi-label instructional learning. To approach to learn common kernel representation that describes AU correlations. 2 ways to solve these issues are capturing correlation through fully connected layers, inferring structures through probabilistic graphical models. In the research paper, they had a couple of researchers talk about what they did, and one of them, or 2 of them, proposed, while existing methods capture local pairwise action units, but their dependencies on another research. And that research was using a restricted Boltzmann machine that captured high-order action unit interactions, and then using patch learning, it used positive and negative competitions among the action units to model a discriminative multi-label classifier. And Kevin will continue on from now.
So with all with the problem we talked about, the researchers came up with a solution, and it was to create a deep neural network, and this would address both patch learning and the multi-label instructional learning. So what this network would do would it would find a way to through it would find a way to address the problem. It would this network would be able to learn 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 new things as it would encounter problems. So as a problem would come, it would have a problem at first, but it would know how to fix it and if it came again. So this model would start by learning local and holistic representations from facial patches. Then after, it would capture the structure between patches by predicting specific action units. And finally, finally, action units correlations are captured by a structure inference network that replicates messages passing inference algorithms in a connection fashion. And what they came up with what they came up with was this deep structured inference network, which or DSIN, and the picture you can see is just a breakdown of what it is. So what it would do is it would take an image and then each input image is cropped into a set of patches, which is used for training an independent CNN, which is a convolutional neural network. And this is just basically a network that analyzes visual imagery. So after it takes the image and crops it into a set of patches, it would produce a probability vector, which you can see over here, P1, P2. And from this vector, patch predictions would be produced, and you could get a combination of these action unit predictions. And then final predictions are computed by inferring structures among action units through iterative messages passing, similar to inference in a probabilistic graph model. And this is just the algorithm they use to train their network, DSIN. And you can see they put in training data, and then there's a model parameters which are set, so patch prediction, fusion, structural inference. And then just by looking at the steps, you can see how DSIN computed each and every action unit. So step 0 would be random initiation around 0. And then step 1, it would train the patch prediction. And next step would be freezing patch prediction. And then now it would train the fusion. And then next step 3 was train patch prediction and fusion jointly. Step 4 would freeze the patch prediction in fusion and would then go on to train structure inference. And then step 5 is training all, and then what you would get would be an optimized parameter of an action unit you can get. And so they had, this is their data they got from testing with other action units, and then you can see in the top right is the action units they tested with, basically, and there's 15 of them. And then the table below is just comparisons between other models, and then you can see that theirs is probably the best or second best one, as you can see that the bolds indicate best results and the brackets indicate second best. And if you look, DSIN has a bunch of bolds and brackets around indicating that it has a better action unit recognition percentage for the given data they used. And then in conclusion, they found that their neural network DSIN is better than the other state-of-the-art methods, BP4D and DISA, for instance, on the BP4D and DISFA datasets. So they got 5.3% better average than other methods on BP4D and 8.2% average better on DISFA. And also the DSIN end-to-end trainable and improves, so it improves on the go. And they are still going to be working on their network. So they said that future work includes learning patch structures at feature level in the structure inference module with increased capacity for output structure learning. And that's it for our presentation. Thank you.